between martingale. So that's also. Um, so we have defined this thing. Okay? We have defined adaptive semi-definite measurable. Okay. So now so do one example. So the sequence of coin toss. And let triple be sigma algebra uh, generated by X. Uh, for each of the following, find the smallest n such that the event belongs to. So consider A is the fast occurrence of heads. Distributed by no more than B. There is at least one head in the sequence x1, x2, So x1, x2 is the sequence of coin tosses, okay? And f can be the sigma algebra generated by so x1, x2, xn be the sequence of coin tosses and let fn be
Sir, I have doubt, sir. Like X1, S2, and Xn, these experiment doing one time say after each one. Like first we toss X1, after that X2, after that X3. Like that, yeah, we toss all the coins at one time.
no, no, you can continue to toss one single coin, okay?
Okay,
Okay.
okay, sir.
So last time we have done one example, right? That
Yes, sir, yes, sir.
first 4 point toss. It is not that you are tossing the coin together. You are tossing the first coin, second. If it's a fair coin, then first coin, second coin, third coin means that you are tossing a single coin first time, second time. It's the same, right? Because
Yes, sir, yes, sir.
yeah, and you notice the outcome. Correct. So mhm. X1, X2, Xn is a sequence of coin tosses means you toss the coin and note the outcome, head or tail. And then you toss the coin second time and note the outcome. So yeah, the first occurrence of heads preceded by no more than 10 tails, right? So, and the second one is there is at least one head in the sequence of this thing. Okay. So yeah, so how to see this thing? So first one is the first occurrence of head preceded by no more than 10 tails. Okay, right? So first occurrence of the thing preceded by 10 tails. So that means you have 10 tail and then a one head. At least no more than 10 tails. So that means max first occurrence of heads preceded by no more than 10 tails, right? And that is what you have. First occurrence of heads preceded by no more than 10 tails. Correct. So that means here first occurrence of head preceded by no more than 10 tails. That means maximum 10 can be there, right? Maximum 10 tails can be there, right? So, so the what will be the smallest n such that the event belongs to Fn? And the event A should belong to which one? F10 or F11? Anyone? So the
Sir,
first one,
it's saying कि our first aid comes not should be come after like 10 tails. Then it should come after one tail also.
yeah, it can come after one tail also. Yes.
So then it can belong, sir, A1, A2, F1, A2, F2 also, sir. A belongs to F1, F2.
Yeah, that can get belongs to the first occurrence of heads preceded no more than 10 tails. So no more means maximum 10 tails can happen. So the first occurrence can also, what you are telling is correct. You can have F1, F2, but for this event, the question is what is the smallest 10, right? Suppose in the experiment the first hit comes after 10 tails. First 10 tosses are all tails, and then head comes. Then also that will also be the in A, right? That also,
Yes, sir.
yeah.
Yes, sir. Yes, sir. Then it belongs to F11, sir.
Yes, it should be belongs to F11.
Yes, sir.
It should belong. And what about B?
Uh,
There is
sir,
at least one head in the sequence of x1, x2, this sequence.
B belongs to F1 also, sir. F1.
It may happens to be one, there is at least one head in the sequence, right? But at least one head. So that means, so which guarantees? I mean, you can have a head in the first toss. You can have, you cannot have. You may have a toss in. I mean, you say something so that it guarantees. I mean, for example, when I say in the first one A belongs to F11, the even is guaranteed in F. It may happen in F1, F2. What you told is correct, but my event is no more than 10 tails. So at maximum you have a 10 thing and then you have a head. So I told that A belongs to F11. Similarly, B belongs to F1. B may belongs to first toss, may be head. But second toss may be head, may not be head. Third toss may be head, may not be head. Nothing guarantees, right? I mean, that can you say that okay, five tosses, fifth toss will be a head? Can you say that?
So there is nothing confirmation, sir. We can't say directly, sir.
Yes. So in a sense that so in a sense that mm, so so in a sense that B does not belong to Fn for any n. Right? I mean, you cannot fix a n such that for smallest n such that B belongs to Fn. Correct? Right?
Yes, sir.
So and suppose I give for the same thing I give another this thing another example. So suppose C uh, the first 100 tosses produce the same output. So first, so we are looking for Fn, right? Smallest in Fn. I mean, what is my Fn? Fn is should contain all the information about the things till that time, like till nth time. So it's saying the first 100 tosses produce the same outcome. So how do you know? At least you have to toss, I mean, toss 100 times, right? Then only you can then C can be there, right? I mean, see, the first 100 tosses produce the same outcome or not producing the same outcome. So what is the smallest n you have to know so that you can say that C belongs to something or C does not belongs to something, right? So in a sense that C 100, right? You have to toss at least 100 times to know the things, right? Right?
Yes, sir.
So yeah. So now let's do another. So this type of things I think we have done earlier. Rather, so okay. I think we have done this type of things, but anyway, so just is the smallest. We have done smallest sigma algebra. Okay, smallest filtration. smallest filtration such that the sequence so, so this is the smallest filtration. Okay. So if you have f1, so suppose you take n equal to 1, then we have done the thing, right? The smallest sigma algebra generated by a random variable, right? Those things we have discussed earlier, correct?
Yes, sir.
Yeah. So if when n is equal to 1, then we have discussed those things, the smallest sigma algebra generated by these things. Okay. So now it is saying that this is some sort of it is saying that it is some sort of mm, smallest filtration because Fn is sigma algebra generated by x1, x2, xn. Right? So so what does it mean? So this means, I mean, mm, so so this the same thing. I mean, the statement this says implies that if suppose if you have G1, G2, right, uh, is another filtration, another filtration. So that means it is another filtration means what is so x1, x2 is uh, is uh, is G1, G2 adapted, right? But then uh, if n is contained in Gn for each n, because that is what it says, right? This is the smallest filtration, smallest filtration. That means if you have another filtration, suppose G1, G2, these things, then I mean, Fn should be contained in Gn for each n. That is what it says. Mhm. Okay. So, so yeah. So how to discuss how what so Just a moment. You see, you discuss this. Fn, this last line, you see that Fn contains all information about x1 to xn, right? Fn contains all information about x1 to xn. So this is important to note that. I mean, so Fn contains all information about x1 to xn, right? And yeah, so correct. And also this the first line, if you see that Fn represents our knowledge at time in. So so that means that Fn contains all the information about x1 to xn. Right. Now, if we see this exercise, the new exercise class. Yeah.
No, no, no.
So you want to discuss that?
Wanted to see if you can open the form.
Yeah, this is open. Just a minute.
Ah,
Yeah,
you
but
can open it, you can see it, you can edit. No,
edit or not edit, I don't know.
no, you can. See that.
Yeah.
So, all three forms you saw. No?
Yeah. No, the first one, the last two one you said by that time I started. So, yeah, I have the comments, but maybe we discuss during the meeting also,
Yeah,
because all of people will be there.
Yeah. And I think, okay, we discuss.
Yeah. Hello?
Yes, sir.
Yeah. Okay, so yeah, so just a moment. Yeah, so what we are discussing, so if G1, G2 is another filtration such that X1 this is adapted to them, then Fn is this thing, right? So so in a sense that so what we have, so what we have, Xn is Gn measurable, right? Gn measurable for each n. Correct. So and Xn is Gn measurable, and also Gn is a filtration, right? So just a moment, is it given that filtration? I just want to check. Yeah, so this is also another filtration. Correct? This is another filtration such that this is adapted to this thing. Okay, so this is another filtration, right? So if it is another filtration, so filtration means what? Filtration, we have seen the definition of filtration, right? So filtration means, yeah, this is the definition of filtration, that F1 contains increasing sequence of sigma algebras. The simplest definition of filtration is increasing sequence of sigma algebras. Okay? So, so, yeah, so increasing sequence of sigma algebras. So now Gn is also say this thing, right? Because Gn is also a filtration, right? So this means G1 contained in G2, contained in G3. This one, right? It goes on. Correct? And so filtration. So in a sense that X1, X2, this thing, Xn is Gn measurable, right? Correct. So Gn contains all information of X1 to Xn, right? So these are Gn measurable for each n. Correct. So Xn Gn measurable of each n. And what is the definition of Fn? So Fn is the sigma algebra generated by this thing, right? So generated by this one, correct? Sigma algebra. So by definition, Fn by definition is nothing but right. Correct. Now yeah, Fn, this is the definition, this is given, right? This one, so this one is given that Fn is sigma algebra generated by this. So in a sense, it's given that sorry, X1, X2, Xn. I mean, is element of Fn maybe not correct, but are Fn measurable? Right. So this is given that this is Fn measurable. And you show that this is also Gn measurable. I mean, something is contained in, I mean, X belongs to A. If X belongs to A implies X belongs to B, then we say then A is contained in B, right? This is my definition, right? Right? When can you say that something is, this is my definition of this thing, right? And so this X1, Xt, these things are Fn, and Fn is by definition is this one. And you show that this is belongs to also this Gn measurable. So in a sense that Fn is Gn for each n. So that is what we have to show, that Fn is contained in. Okay. Now we define the martingale. We will define the martingale. What is a martingale and all? Because yeah, hmm. Yeah. So it has martingale has um, application. Okay? So it has a lot of application like. So it's mainly related to the gambling. Okay. So related to favorable, unfavorable games of chance. So it's mainly the gambling. So it has many application in finance and financial derivatives like options and all. And so it has a huge application. I mean, it has huge applications. We'll define this thing. Define the what is a martingale? Definition. So a sequence of random variables is called a martingale with respect to a filtration um, uh, Vexen is integrable for each n belongs to n. Okay. Number one. Number two. X1, X2, dot, is adapted to F2. Number three. This is the yeah. So martingale. What is a martingale? Martingale. So this is a definition of the martingale. Okay. A martingale you define always with respect to a filtration. F1, F2.
What is third term E of X N S one? What is this one, sir?
So expectation of x, conditional expectation of xn plus 1 with respect to the sigma algebra.
Okay, sir. Okay.
Fn. That's what we have done. We have spent so much time on sigma conditional expectation because it has a huge applications in that. So expectation of xn plus 1, and this is one of the main property that so so xn is integrable with respect to each n. So the integrability required because you are doing conditional expectation. Okay, so you need the integrable condition. And then x1, xi is xn is fn measurable. That is xn is fn measurable. That is for the second one. And third one is the most. This is actually gives a gives something very important, that expectation, conditional expectation of xn plus 1, right? You are taking a conditional expectation of xn plus 1, conditioning over fn. Okay, so you have all the information till nth information, and you want to see about something, you want to know something about the n plus 1 state. It is not that this is giving you the value of n plus, you can have a value of the n plus, you have all the information till nth stage. It is not that you are getting exactly the n plus 1th stage things. No, it is the conditional expectation of xn plus 1 given fn, whatever the information you have is equal to xn almost sure. Okay, so in a sense that it gives certain predictable nature of the future. It gives certain properties of the these things. So yeah, so in a sense that a conditional expectation. You so suppose you have the you know the price of a stock of last 180 days, right? And then you want to you want to get something, or you want to predict something about the 181 days. Okay, it is not that it is giving you the exact these things, but it gives you certain properties or certain uh, predictable things of the expectation of xn plus 1 given conditional expectation of xn plus 1 given fn is equal to xn. Xn almost and almost surely, because as we discussed earlier, the conditional expectation is nothing but a random variable, correct? It's a random variable. So an equality of random variable is not pointwise, it is always uh, almost sure, right? Correct.
Yes, sir.
Yeah. So Yeah, so we'll do some examples and all. So yeah, let's take a break and then we'll start. We'll do some examples and okay. Okay, is it okay? Oh. Okay. Hello.
Yes, sir.
Yeah. So I have a question. So is next Monday is your holiday?
Sir, I am not sure. Let me check, sir.
Yeah, please check and let me know.
Yes, sir. Yes, sir. The holiday, sir.
It's a holiday, right?
Yes, sir.
Okay. ठीक है. So 20th is a holiday, right?
Yes, sir.
Okay. Okay, so if it is a holiday, then we'll not have classes next Monday. Okay.
Okay, sir.
We'll have Thursday. Thursday usual we will have, but if it's a holiday, then it's a holiday. Okay, so yeah, so we are discussing the definitions of martingale, right? So the so now we do some examples, okay? Examples or exercise or we do some. Okay, so let x1, x2, okay, uh, be independent and integrable random variable. Mhm. Okay. So yeah, so independent random variables and they are integrable such that expectation of xn is equal to 0 for all n belongs to n. So, so that means expectation of x1 is 0, expectation of x2 is 0, like this. Okay. Okay. Let now let you define yn, right? Such that x1 plus x2 plus dot plus xn. Okay. I define another random variable yn such that x1 plus x2 yn is nothing by definition is x1 plus x2 plus xn. Okay. Okay. And okay. And fn you defined as sigma algebra generated by x1, x2 total. Okay. Okay. Fn is what? Sigma algebra generated by x1, x2, x. Now y1, yn is x1 plus x2 plus xn. So in a sense, what you can conclude that therefore yn is fn adapted, right? Correct. Because what is yn? Yn is nothing x1 plus x2 plus xn, right? So, I mean, f1 is sigma algebra generated by x1. So, y1 equal to x1. So, y1 is f1 adapted. And similarly, f2 is sigma algebra generated by x1 and x2. And if you take y2, y2 is nothing but x1 plus x2. So, therefore, y2 is f2 adapted, right? So, and now so this is yn is fn adapted. Now whether yn is integrable. Now the question is yn is integrable. X1s are integrable is given, right? Expect xn is integrable, xn's are integrable is given. Now, and an expectation of xn is 0. Now, something random variable integrable or not, what you have to show? You have to show that expectation of yn, this is finite, right? That is what you have to show. Correct? That is what you have to show. Something is integrable or not, this is the definition that you have shown that the expectation of x is integrable. That means expectation of mod x is finite. Right? That is what the definition of integrability tells you, right? Correct. So now what is expectation of yn? So by definition, yn is nothing x1 plus x2 plus plus xn, right? And so this is mod of this one, right? And I can use the triangle inequality, correct? So I can use the triangle inequality to say that I mean, triangle inequality is like this. I mean, you have mod a plus b less than equal to mod a plus mod b, right? This is my triangle inequality. And you can do it for, like, suppose a plus b plus c, right? So you can do first mod triangle inequality for these two things. So it is less than equal to mod a plus b plus mod c. Again, you do the triangle inequality. Here is mod a plus mod b plus mod c, right? So this is my triangle inequality. So triangle inequality. So this is the way you use it for any finite number of things. Okay, so okay, so I have used the triangle inequality here, and then my another thing is the expectation is linear, right? Expectation is linear. So expectation is linear. So it is so therefore expectation of x1. Sorry. X1 plus expectation of x2 uh, plus dot plus expectation xn. Right. Now, what is given to you that this is x1 be independent and integrable random variable, right? It is given to you that this is integrable. So integrable means expectation of xi is finite for every I. What is given that expectation of xn is zero. Expectation of xn is zero is okay, but for integrable definition is expectation this is finite. Mod xn is finite. Okay. Expectation of mod xn is finite. It does not say that expectation of xn is finite. Okay. So this is the integrability definition. So yeah. So now, so for each one, each xi is finite. Expectation of xi is finite, and you have a finite sum. You have n sum. So therefore, this is finite, right? Each one is finite, and you have a finite sum. So therefore, this is finite. So in a say, therefore, so this implies yn is integrable. Integrable. Okay? Yn is integrable. Okay. So first thing we have shown that first thing is yn is fn adapted, and then we show that this is yn integrable. Okay. Now we are looking for, now we want to evaluate we want to evaluate this. Okay. Either you want to evaluate, or you can say that yeah, you want to evaluate this, or you can or show that this yn is a martingale. So yn is a martingale. So to show that yn is a martingale, what you have to show that yn is integer. So if you what you have to show all these three properties, right? Yn is integrable for each n, yn is fn adapted, and the last one, right? and the last one. Now we have shown that this is adapted. Adaptedness we have shown. The integrability we have shown. And now the last one we have to show. Okay. Okay. Now how you do that? So expectation yn plus 1 given f. Expectation yn plus 1 given. Okay. Now what is this fellow? So this one I can write it as yn plus xn plus 1, right? I can write this. So yn plus 1 is yn plus xn plus 1, right? So yn plus expectation, please. And or I mean, if someone can write it more rigorous. I mean, if you want, if you have any problem, you can just write it. You can see it this way. I can write it in this way. So in a sense that, so yn plus 1 by definition x1 plus x2 plus dot 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 plus xn plus xn plus 1 given fn, right? Right. And and this is till xn, this is by definition yn, right? This is by definition yn. So therefore I can write this one, expectation yn plus xn plus 1 given fn. Now we will use the properties of the conditional expectation. Okay, properties of the conditional expectation. And what is the first is we know the linearity property of this thing, the expectation of ax. So we have done certain properties. So these properties, you see the first property, expectation of ax plus by given g is nothing a into expectation of conditional expectation of x given g plus b into conditional expectation of y given g. Okay, I will use this first step. I'll use this step. So this is expectation yn given fn, right? Plus expectation xn plus 1 given f. Okay. Now I have expectation of yn plus 1, yn given fn, and expectation of xn plus 1. Conditional expectation of xn plus 1 given fn. Now we will use so yn given fn. Okay, so what we have proved already, yn is fn measurable, right? We have proved that yn is fn measurable. or yn fn adapted. That is already we have shown. And from the conditional expectation properties, sorry, from the conditional expectation properties is yeah. So you see that this first one, that if x is g measurable, then conditional expectation of x given g is x. This is the first property, right? Expectation of this property, that the first one, that expectation condition x is g measurable, then conditional expectation of x given g is nothing but the x, right? So I use this property. No. So so just so this is x almost sure, right? So therefore this will be, so this will be yn, right? And this, what about the second part, that expectation of xn plus 1 given fn? So what is given to you, that xn's are independent random variable, right? Xn's are independent random variable. So, and fn is the sigma algebra generated by x1 to xn, correct? Fn is a sigma algebra generated by x1 to xn, and xn's are independent and xi's are independent random variable. So in a sense that x, so we can say in a sense that xn plus 1 is independent of fn, right? And now again I go back to the conditional expectation properties. Okay, I again go back to the conditional expectation properties. So what is that? That you see this property, this first, second, third, fourth property. You see this fourth property, that if x is independent of j, then conditional expectation of x given g is nothing but an expectation of x, right? So I use this property, okay, and so this is expectation of x. So expectation, sorry. X correct. Expectation of xn plus 1. Okay. Expectation of xn plus 1. Now what is given to us is that that expectation of xn is 0 for all n, right? So therefore this part is 0, correct? So what we have is nothing but yn. And all these things is almost surely, right? Because the conditional expectation, all the properties holds almost surely. So this is almost surely. And therefore, so what we have shown, that expectation of yn plus 1 given fn is nothing but yn almost surely. So this implies that yns are nothing. Because first you prove that this is adapted, then you show that this is integrable, and then you show the third property. So therefore, this is the Mach number. Okay. ठीक है.
Yes, sir.
Okay, so I have to go to a meeting. Okay, so I have a meeting. So let's meet on Thursday. Okay.
Okay, sir.
Yeah, so let's meet on Thursday. Okay. Thank you.
Okay. Thank you, sir.